Section 3.9. Inverse trigonometric functions. The outline of this video is as follows. We will discuss the inverse trigonometric functions, starting from the ground up with their formal definitions, domains, and ranges. From there, we will visualize these functions by examining their graphs and exploring their important properties, which will help build our intuition. I will also point out a specific caution regarding the definition of the inverse secant of x, as its range can be defined in a few different ways. After establishing these fundamentals, we will move to the core calculus topic, deriving the formulas for the derivatives of these inverse functions. Finally, we will conclude by reviewing some key identities and summarizing the most important takeaways from our discussion. This path will give us a complete toolkit for working with these essential functions. In this section, we will complete our toolkit for inverse trigonometric functions, moving beyond the two we have already seen. While we have focused on arccosine and arccosine before, we will now formally define all 6 inverse trig functions, including arctangents, arcotangents, arcsecant, and arcosecant. I will start by explaining how their domains must be restricted to ensure they are true functions, which is a crucial first step. Then, we will visualize their behavior by examining their graphs and practice finding their values for specific inputs. The main goal, however, is to learn how to find their derivatives, which are surprisingly common in calculus. For example, knowing the derivative of arctangent is essential for solving certain types of integrals later on. By the end, you will have a complete reference for defining, evaluating, and differentiating all 6 of these important functions. Let us explore the remaining 4 inverse trigonometric functions, which are all designed to answer the question, what angle produces a given trigonometric value? Just like any inverse, their graphs are created by reflecting the graphs of the original functions across the line y equals x. For this to be possible, we must first limit the original functions to a restricted domain where they are 1-to-1. For example, the arctangent of a number x is the specific radian angle whose tangent value is x. This means the arctangent of 1 is the angle pi over 4, because the tangent of pi over 4 is 1. This restriction is crucial, because without it, a single input would map to infinitely many possible angles. The key takeaway is that each inverse trigonometric function takes a ratio as an input and gives you back a single, unique angle from a carefully chosen interval. Now let us establish the formal definitions for the remaining 4 inverse trigonometric functions, which center on carefully choosing a specific range of output angles for each one. The arctangent of x is the angle y in the open interval from negative pi over 2 to positive pi over 2 whose tangent is x. Similarly, the arcotangent of x is the angle y in the open interval from 0 to pi whose cotangent is x. The definitions for arcsecant and arcosecant involve intervals with a single point removed. For arcsecant, the angle is in the interval from 0 to pi, but specifically excludes pi over 2. For arcosecant, the angle is from negative pi over 2 to positive pi over 2, but excludes 0. We must exclude these points because the original functions are undefined there. For instance, the tangent of pi over 2 is undefined. These precise ranges are chosen to guarantee that each inverse function gives a single, unique output angle. Let us examine the key properties of the arctangent and arcotangent functions, which define their unique graphical behavior. The arctangent function can accept any real number as an input, so its domain is from negative infinity to positive infinity. Its output, however, is restricted to the open interval from negative pi over 2 to positive pi over 2, which causes its graph to have 2 horizontal asymptotes. For example, as the input x becomes extremely large, the output angle approaches pi over 2. Arctangent is also an odd function, meaning its graph is symmetric about the origin. In contrast, the arcotangent function also has a domain of all real numbers, but its range of output angles is the open interval from 0 to pi. Unlike arctangents, the arcotangent graph has no simple symmetry. The most crucial takeaway is the difference in their ranges. Arctangent gives angles in quadrants 1 and 4, while arcotangent gives angles in quadrants 1 and 2. Now I want to address a tricky detail about the inverse secant function, because its definition is not universally agreed upon. For negative values of x, different textbooks choose different intervals for the range. In our work, we will define the range of inverse secant to be the interval from 0 to pi, excluding the point pi over 2. The main advantage of this specific choice is that it preserves a very useful computational identity. The inverse secant of x equals the inverse cosine of the quantity 1 over x. You should be aware that other resources might define the range differently, which can simplify the formula for the derivative but breaks this important identity. So the thing to remember is that our definition maintains consistency with the inverse cosine function. Let us find the derivative of the inverse sine function, a fundamental rule you will use often. First, notice that the inverse sine function is differentiable on the open interval from -1 to 1, because its graph has vertical tangents at the endpoints where a derivative is not defined. We begin the derivation using the inverse function theorem, which gives us 1 over the cosine of the inverse sine of x. To simplify this, we use the identity that the cosine of an angle is the square root of the quantity 1 minus the sine squared of that angle. Since the sine of the inverse sine of x is just x, the expression simplifies nicely. This leads to our final result, which, when combined with the chain rule for a function u, states that the derivative of the inverse sine of u is 1 over the square root of 1 minus u squared, all multiplied by the derivative of u. The essential rule to remember is that the derivative of inverse sine of x is 1 over the square root of the quantity 1 minus x squared. Now let us see how to combine our new derivative formula for inverse sine with the chain rule. We want to find the derivative of the inverse sine of x squared. The key is to recognize that the inner function, which we call u, is x squared, and its derivative, du dx, is 2x. The general formula states that the derivative of the inverse sine of u is 1 over the square root of the quantity 1 minus u squared, all multiplied by du dx. Substituting our expressions, we get 1 over the square root of the quantity 1 minus the quantity x squared times 2x. Since x squared is x to the power of 4, our final result simplifies to 2x divided by the square root of the quantity 1 minus x to the power of 4. The main takeaway is to always remember to multiply by the derivative of that inner function. Now let us find the derivative of the inverse tangent function, which has a surprisingly simple and useful result. We will again apply the inverse function theorem, which uses the reciprocal of the derivative of the original function. The derivative of tangent x is secant squared x, so our expression becomes 1 over the quantity secant squared of the inverse tangent of x. To simplify this, we can use the Pythagorean identity that secant squared of an angle is equal to 1 plus the tangent squared of that same angle. This transforms our denominator into 1 plus the quantity tangent of the inverse tangent of x, all squared. Since the tangent and inverse tangent functions cancel each other out, this simplifies beautifully to just 1 over the quantity 1 plus x squared. A key feature here is that this derivative is defined for all real numbers. The final chain rule form is that the derivative of the inverse tangent of u is 1 over the quantity 1 plus u squared, all times du dx. Now we will find the derivative of the inverse secant function using implicit differentiation. We begin with y equals inverse secant of x, which we can rewrite as secant of y equals x. After differentiating both sides with respect to x, the chain rule gives us secant y times tangents y times the derivative dy dx equals 1. Solving for the derivative yields 1 over the quantity secant y times tangent y. To get this back in terms of x, we substitute x for secant y and use a trigonometric identity to replace tangent y with the square root of x squared minus 1. This creates a sign ambiguity, but looking at the function's graph reveals its slope is always positive. We enforce this by placing an absolute value around the u in the denominator, giving our final chain rule formula. The derivative is 1 over the absolute value of u times the square root of u squared minus 1, all times du dx. Now that we have the derivatives for arcsine, arctangents, and arcsecant, we can find the derivatives for the remaining 3 inverse trig functions using a clever shortcut. This method relies on the cofunction identities, which state that an inverse cofunction like arcosine of x is equal to the constant pi over 2 minus its corresponding inverse function, arcosine of x. To see how this works, let us find the derivative of arcosine of x. We simply take the derivative of the right side of the identity, which is the quantity pi over 2 minus arcosine of x. The derivative of the constant pi over 2 is 0, so the result is just the negative of the derivative of arcosine of x. This gives us negative 1 over the square root of the quantity 1 minus x squared. The key takeaway is that the derivatives of the inverse CO functions are simply the negatives of the derivatives of their corresponding inverse functions. Here is a complete summary of the derivatives for all 6 inverse trigonometric functions. I want you to notice a powerful pattern that makes these much easier to learn. The derivative of each cofunction, like inverse cosine or inverse cotangent, is simply the negative of the derivative of its corresponding function. For instance, the derivative of inverse sine of u involves the positive square root of the quantity 1 minus u squared in the denominator, while the inverse cosine derivative is identical but with a negative sign. The same relationship holds for the inverse tangent and cotangent pair, and for the inverse secant and cosecant pair. Remember that the du/dx term in each formula is just the chain rule in action for when u is a function of x. So, the key takeaway is that you only need to memorize 3 of these formulas, and you get the other 3 for free just by adding a negative. Let us summarize the key ideas for inverse trigonometric functions. To create these functions, we must first restrict the domains of the original trigonometric functions to make them one-to-one, which in turn defines the specific domains and ranges for their inverses. The definition for arcsecant, for example, is chosen specifically to maintain the useful identity that arcsecant of x equals arcosine of the quantity 1 over x. When we need to find derivatives, our new formulas work directly with the chain rule to handle compositions, such as the arctangent of a function u of x. Finally, a very helpful pattern is that the derivatives of the inverse CO functions, like arcosine, are simply the negatives of the derivatives of their counterparts, like arcosine. These principles provide a complete toolkit for differentiating all 6 inverse trigonometric functions. To wrap up our discussion, let us review the key derivation techniques we have learned by thinking through 2 important problems. The first challenge is to derive the formula for the derivative of arcsecant of u. This requires you to use implicit differentiation on the equation secant of y equals u, and then use a trigonometric identity to express the result purely in terms of u. I want you to also consider the graph of the arcsecant function. Its always positive slope is the visual reason we need the absolute value in the final formula, which is a key insight. The second problem asks you to find the derivative for arcotangents using 2 different paths. You can either apply implicit differentiation from scratch, just as we did for the other functions, or you can use the identity that relates arcotangents to arctangents. The second method provides an elegant shortcut by reusing a result we already established. I highly recommend pausing to work through these problems, because deriving these rules yourself is the most effective way to understand why they work and to commit them to memory.